Okay, the next type of projectile motion problem we're going to work on is projectile motion type 2. Type 2 is different than type 1 for a couple reasons. So first off, you're starting and landing at the same elevation. In this case, it's on the ground, but it won't always be that way. So you're starting and ending same level. So if you look at this, when an object is thrown and lands at the same level, it looks very similar to your freefall arch, which is on the front of this packet. So if you flip back to that front of the packet, you can see that the velocity at the top is 0. Remember, the acceleration throughout is negative 9.8 in terms of the y direction. And then again, with the y direction, the velocity is positive when you're going upward and negative when you're going downward. All these things will come into play at some point when you're working with type 2 projectile motion problems. So let's read this through and see what we can do. A ball is thrown at 10 meters per second at an angle of 20 degrees above the horizontal. How far away will it land? How high will it go? So since this ball is being thrown at an angle, I first draw a vector to kind of display that motion. Now 20 degrees is kind of a tight angle, so mine's probably not 20 degrees, but you get the visual. Draw a vector on an angle. Then what you're going to do is label that vector. So this vector I'm going to label as 10 meters per second, and that is the initial velocity that the ball is thrown at. So that's going to be my VO. We're not going to put an X or Y on there because we have to break this angled vector, angled velocity, into its X and Y components. The reason for this is we work in 1 dimension or 2 dimensions. We don't break into any other axis in this level of physics. So we're going to break this down into what we can understand, translate it into 2D. So let's do that before anything else. I can turn this into a right triangle by drawing an x-axis down here. That will be my V initial in the x direction, and then my y direction I can draw like so. This allows me to then label my angle of 20 degrees. So this is what a good vector diagram would look like when you are working with a projectile motion problem like this. So you want to make sure to have your x and y components defined after you initially draw your angled vector. So the next thing you're going to need to do is come up with formulas to solve for your x and y components. So just to have a little background, reach back in our brains to a little bit of geometry. If my angle is where it is, this side would be the opposite, this side would be the adjacent, and then opposite that angle over here, I'll put a little O, and then my hypotenuse is always my longest leg, okay? So in order to solve for my x and y components, I need to use my trigonometric functions. So for Vx, I have to decide if I'm going to use SO, CA, or TOA. Really sine, cosine, or tangent. But writing them like this helps me realize what function I need to use. So I need to solve for my x direction, that is my adjacent. I won't be using sine because it doesn't have adjacent, and I won't be using TOA or tangent because I don't have my opposite defined. I have letters for it, I have variables, but I don't have any numbers. So the only thing I can use is cosine. So cosine of theta is equal to opposite over hypotenuse. So the adjacent over hypotenuse. So the adjacent in this case is V in the x direction, initial velocity in the x direction, divided by my overall initial velocity. I'm going to rearrange that so that I'm solving for my initial velocity in the x direction. And then I'm going to do the same thing over here for my y. So to solve for my v in the y direction, I'm going to say I'm going to use sine. Reason why I'm using sine is slope, and I'm using my opposite side, and I have my hypotenuse. Therefore, sine will do the job. Sine of theta equals my opposite, v initial in the x direction, divided by my overall v initial. Just gonna draw a little line in the middle to separate them. I'm rearranging and getting my initial velocity in the y direction alone, so I have to multiply by VO on both sides. I'm skipping writing any of the intermediate steps, so hopefully you're following. So now I have two formulas to solve for my initial velocity in the x direction. So how fast am I going horizontally to start? And then how fast am I going vertically to start? The next thing you're going to do is just plug in your numbers. So over here, I have 10 meters per second times cosine of 20 degrees. Continuing that line, and then over here, I have 10 meters per second times sine of 20 degrees. So I'm going to go ahead and plug that into my calculator right now. When I go to use my calculator, I gotta make sure that I am in degrees to begin with. So I click on mode, and then I scroll down, and I see that I'm in degrees. I quit, and I'm good to go. So 10 cosine of 20 gives me 9.39. So I'm gonna round that up to 9.40. 3 significant figures is usually good enough. And then 10 sine of theta gives me 3.42. Remember, these do have units because we're solving for velocities right now. With these formulas, or these problems really, sometimes you can lose track of what you're actually solving for, so the units give meaning to the numbers. Make sure you tow them around. So what I'm going to do after this is start collecting all of my givens. So we just did one big precursor step where we broke everything down into x and y components so that we could start solving this problem. I'm going to list all of the givens I know. So in the x direction, acceleration is 0 meters per second squared. Because we have no air resistance, we will never have air resistance in this class. And then in the y direction, gravity coming through with negative 9.8. I'll list off all of my givens. So remember, position is still x in the x direction, but it is y in the y direction. And then to modify our velocities, we just throw a little subscript on, depending on if it's in the x or y direction. And time's just chilling. It's in both categories. And I should put a little x and y on my accelerations as well. So now that I have all of these listed off, I'm going to start filling in. I have my initial velocities in the x and y direction down below. So my initial velocity over here in the x direction is 9.40 meters per second. Over here in the y direction is 9.42 meters per second. In my x direction, I have no change in velocity because there's no acceleration. So I'm going to just copy my velocity down because it's going to stay the same the whole time. The next thing I need to decide is if I have any other kind of constants, right? So I know that in my x direction, usually my initial position is 0 meters. It doesn't indicate anything otherwise that would make me think I'm starting at like the 10-meter mark. So I'm going to assume it's 0 meters. The next thing that gets a little tricky is we are solving for kind of two parts of the free fall arch here. So the first question here says, how far away will it land? And then the second question says, how high will it go? So we're asking for information when we're at our highest point and information when we're at the end. So we have to have givens for two separate scenarios. So let's start with solving for the time to get to the top. So how high will it go? I'm going to fill in my information in this top section here as if I am only solving for this component. So if I'm only solving for this component, my velocity at the top is going to be 0 meters per second. So I have an acceleration, an initial velocity, a final velocity. I can use this to solve for time. If you remember from our last situation, we said that time is what marries the entire problem, right? It marries the x and y components. So I'm going to first solve for the time that it takes me to get up to the top of my arch. So I do this by using my first kinematics formula. The reason I'm doing this is I don't have any position information for my y direction, and I only have velocity, acceleration, and solving for time. So I rearrange this, cancel out anything that's equal to 0. In this case, my final velocity is equal to 0. I messed that up. Make sure you're writing for the y direction. So my final velocity is equal to 0, and that is pretty much it. So when I rearrange this formula, I get the opposite of my velocity initial in the y direction divided by my acceleration will tell me my time. So I'm going to check back, see if I have a negative. I have a negative in my acceleration, so we're good. That should cancel out the negative up top here. I'm questioning because I have time that I'm solving for, and my time can never be negative. So you should always question yourself if you feel like you're about to get a negative for time. Something definitely went wrong. Next thing I'm going to do is just plug in. Okay, so 3.42 divided by negative 9.8. And I get 0.35 seconds. So 0.35 seconds doesn't equal just my time. It equals my time up. If you remember from your free fall problems, time up equals time down. This will come into play later when we try to solve for the second question here. Let's stick with solving for how high this object is going to go. So now we have time. I can come up here and I'm going to add it in, but I'm going to define it as time up. 0.35 seconds. Now I want to solve for my final position. In order to solve for my final position, I don't have an initial position written down yet, but I can say my initial position is 0 meters. So we missed that one before. That's okay. So to solve for my final position for the highest point, I can use pretty much any formula except for the first one. So I could use 2 or 3. I'm just going to pick 2. So y equals y initial plus v initial in the y direction times time plus 1/2 acceleration in the y direction times time. My initial position is equal to 0, and that's pretty much it. So my initial velocity in the y direction is 3.42. My time is 0.35 seconds. My acceleration is negative 9.8 meters per second squared. And again, my time is 0.35 seconds. All right. So I'm going to plug this into my calculator. I got 3.42 times 0.35 plus, I'm going to change that half to a decimal, negative 9.8 times 0.35 squared. All right. So I get my y value equals 0.60 meters. So this is one of my answers. I'm going to highlight it, but on your paper you should just circle it. And I'm going to come back up here, cross that out, and just add in my given. Okay, so that solves for one answer here. How high will it go? Check. Now, how far away will it land? Again, time is always going to help us start solving these. If my time up is 0.35 seconds, then I know my time down is also 0.35 seconds. So to solve for my time, I'm going to do 2 times 0.35 seconds. That's going to give me my overall time up and down. And when I'm asking myself, how far away did something land? I'm asking after the entire situation, how far away did it land? So my time to reach my furthest distance horizontally is 0.70 seconds. So now to solve for my distance away horizontally, I can plug that time and all of my given values into whichever kinematics equation involves distance. Again, I'm just going to choose number 2. My initial position is 0. My acceleration is 0. So all in all, I only have to multiply 2 things together. My initial velocity in my x direction, which is 9.40 meters per second, times my time. Again, I'm talking about overall time it takes to travel, so 0.7 seconds. And I find that the distance I'm going to go is 6.58 meters. That is my horizontal range. So overall, we have a good amount of work written down here. You want to make sure you just circle your answers and make it very clear that those are your answers. Sometimes it's hard to keep these problems very organized, but do your best, and circling your answers will definitely save you in the end. Sometimes there'll be problems that have you like fill this in at the end, but for our skill building problems, it's good as is. So what I want you guys to do now is try out the skill building problems assigned and see what you could do. Have a good day.